My name is Sugu. I work for YouTube at Google. I'm part of the Vitess team. Those of you who don't know what Vitess is basically the storage solution that we use to scale to scale at YouTube. It supports replication and sharding. It's still under active development. We are not completely feature complete, but we are still using it at YouTube. We are already using it at YouTube, and probably in a few months' time, it will probably be ready for people to download and use. Our project is open sourced. It's on GitHub. If you go under YouTube, you can see it. And as you'll see, there's lots of things changing there. So I'm not going to talk too much about Vitess itself, but I'm going to talk about some of the rationales we used and why we made whatever decisions we made, why we made whatever trade-offs we made to make sure that Vitess can scale the way we wanted. And to start with, I'm going to talk a little bit about the CAP theorem. How many of you are familiar with the CAP theorem? Okay, a few people. So the CAP theorem, I would actually even call it the common sense theorem. It basically says that you cannot have everything. When you try to scale a system, you have to give up on some things. And it gives you a hint about what you need to give up to get what you want in terms of scaling. So when we scaled YouTube runs on, used to run on MySQL, now Vitess is kind of a layer on. This is going to be interesting.
So what's your take on the difference between ACL and CAP?
Base and CAP, I will talk about it. I actually won't talk about base by itself, but I think it will...
The difference between CAP and ACIP.
Yes, I will talk about that, definitely. I have a slide for that. So what else can I say before I move into the details? I think that's about it. Let's go into some definitions. So the CAP theorem basically, if you have to summarize what it says, is that if you have a distributed system and while your distributed system is performing and there is a network partition, which means that your network breaks down, the system has to choose between delivering or keeping the data consistent, or it has to give up on consistency if you want your system to keep serving data. So that's basically what CAP theorem states. There is even a proof for it. It was formulated by a person called Eric Brewer, who currently works at Google. And when I first heard about it, I was very fascinated because it means a lot if you're thinking about scalability. And so I was thinking about it, I read about it, and there's a lot of misunderstanding about what the CAP theorem really is about. So I'll try to clarify what that is here before I move on to the significance of it in terms of scalability. So the first one on CAP is what it calls as consistency. The consistency as defined by the CAP theorem is actually what is known as the read after write consistency, which means that I write data and immediately turn around and try to read it. Will I get the data that I have written? Or will I get the data that I wrote a few seconds ago or a few minutes ago? So that is what the CAP theorem talks about when it talks about consistency. Typically, it says that if you have a system where you write data and the data gets replicated to other places using network, you write data and immediately try to read it back. If you read it from a replica, the data might not have reached the replica and you may get stale data. That's basically what the CAP theorem is about. It is not same as the ACID consistency that databases talk about. The ACID consistency that the databases talk about deals more with relational consistency where there is a foreign key integrity issue. Those are the things that the database ACID talks about. A lot of people confuse the two to be the same. They are very, very different. As a matter of fact, the consistency in CAP theorem is more closely related to the atomicity part or the durability part of ACID, but actually it doesn't have to do much with the consistency of ACID itself. Actually, the opposite of consistency is what we call eventual consistency, which means that your data that you read may not actually be consistent. So that's the definition of consistency as far as the CAP theorem is concerned. Availability we all know, which means that you request something, the system has to give you a response in a timely manner. If it doesn't give you a response in a timely manner, then the system is not available. The partition tolerance is actually the most confusing part of the theorem. And what is partition tolerance? So the easiest way to talk about partition tolerance is that if your system is partitioned, if your system is distributed, it is not partition tolerant. Which means that if you have two different hardware connected by a network cable, that network is going to fail, and you have to assume that your system is not partition tolerant. So the way I would rephrase this, the CAP theorem, is that you cannot get consistency and availability in a distributed system. That's it. If you want both consistency and availability, then your system should not be distributed. So that is what CAP theorem is. The one caveat is that the CAP theorem doesn't apply to a system as a whole. It applies only to operations that we perform on a system, which means that I can say I want to perform a particular write, and I want that to be, sorry, I'll probably have to keep retyping my password. I didn't know how to disable this. So I will, so I can say, I want this operation to honor consistency more than availability, which means that if I try to perform the operation and there is a partition, it will probably not complete. But if I say I want this operation to be available, then the operation will complete, but you may get stale data. So that is actually a decision that you can make on a per operation basis. It doesn't have to be the property of the entire system.
So how about the difference, in terms of a network, distributed system network? One case is the topology is fixed. The distributed system network topology is fixed. That's one case. The other case is not fixed, which in most of cases is not fixed, because when you scale out, you are trying to change the topology.
Correct, yeah.
But when you are scale up or scale down, that means the topology is fixed. So, for both those two cases, what's your take on?
It doesn't matter whether your topology is fixed or changing. If your system is distributed, you are subject to these rules. The changing topology is kind of orthogonal to the CAP theorem. If you have two different hardware that are connected by a network, you are bound by these rules.
So one more question: for availability in both ACID and CAP, the availability interpretation of availability is exactly the same.
Between
you have one.
So ACID doesn't talk about availability.
Oh, autonomy. Okay, sorry.
As atomic, yes, that's correct. Yes.
Yeah, can we have questions at the end? That would be nice, because I want to have a complete.
Sure, thank you. Sure. Please hold your questions till the end. All right. So everyone is with me so far. All right. So let's look at what is the practical meaning of a CAP theorem and what it does not cover. So if you, the picture here there are two databases and they are connected by a network, but then there are also clients that are also connecting to databases through networks. The CAP theorem, actually, the only failure that it talks about is the link between the two databases failing. If a link between two databases that are replicated fails, then we have to choose between consistency and availability. That's what CAP theorem says. But what it does not talk about are other failures. Like, for example, if a client cannot connect to a database, we don't care about the CAP theorem. Your database is not available, period. There is no data you're going to get if you cannot connect to the database. So this is a failure that it does not talk about. This is another failure that the CAP theorem does not talk about, is if a database itself goes down. It's basically, when it says that a system is available, it assumes that the databases never go down. But these are real failures that we have to deal with, which means that the CAP theorem is itself insufficient for us to make decisions about scalability of a system. There are considerations that we have to apply on top of these things. So let's talk about, there is one more thing I wanted to talk about here. When we talk about a system that is distributed, there are two ways we distribute systems. We either replicate data or we shard it. Again, the consistency in the CAP theorem only deals with replicated data. It does not address sharded data, which means that you wrote data A here and try to read it back from somewhere else. It wants that data A that you wrote to be available on the other end of it. If my data is here and your data is in a different shard and they are being written independent of each other, that is something that the CAP theorem does not deal with. But nevertheless, it is a reality that we have to deal with. Whether the CAP theorem cares about it or not, it doesn't matter. So going back here, so if you look at, when you're thinking about solving scalability, do you really want to partition your data? Do you really want to replicate your data? The primary goal of a system is consistency and availability. Given a choice, you would want everything in one place because then you have all the best properties that you want from the system. But then, in spite of all that, we still go ahead and still replicate our data all over the place, read it from all over the place. So which means that there are other things, other reasons why we want to replicate data, in spite of the fact that we are giving up on consistency or availability. So can you think of some reasons why one would want to replicate data?
It really depends on whether your network topology is fixed or not. Or in other words, whether you are on cloud or not.
Whether you are on cloud?
Oh, yeah, on cloud or not. Because if your network is elastic, then situation will be different.
No, this is about replication. See, why do I want to, after data is written in one place, why do I want it copied somewhere else?
I would want it to have at least a second copy. Think of it as an online backup. It's always there.
Correct. Durability.
Yeah, exactly.
Because if you lose your main database, you don't want to lose everything. You want this data to be somewhere else.
And my recovery time is a lot shorter.
Yes.
You're restoring the backup or using the replicated.
Exactly.
Scalability.
Scalability is another one, which means that if all my reads are going to one database, it's going to get overloaded. If my data is replicated in other places, then I can scale.
Reporting of
Pardon?
You can run a reporting of those replicated databases.
Falling?
You can run your reporting.
Reporting, yes. Offline work, yes. I would call it uptime. Actually, uptime would be more for backup. It's for non-standard load, which actually comes back to scalability.
Could you offer us some of your applications
We'll
background
take
information?
questions afterwards. We are running out of time, so it's question afterwards.
So,
Keep asking us questions.
no, not questions. I'm asking for reasons. So here's actually what I've compiled. If you have more reasons, you can let me know. Durability is something we talked about. Uptime is like when, if I want to back up my data and still want to continue to serve it, then uptime is having a replicated database is useful. As Marty mentioned here, read scalability and latency.
And we can later actually write scalability too.
Yes, I will talk about that as soon as I talk about latency. So latency, if for example, if I have data in US and there are customers in Japan that want to read the data, if this data is replicated in Japan, they will have lower latency. So even though I don't have to replicate data for other reasons, there may be latency reasons why we want to replicate the data. So the right scalability is actually somewhat in conflict with replication. The reason is because you write in one place, what you wrote here has to be written everywhere else. So at some point of time, if you're saturating the disk on your master database, you're also going to be saturating the disk on your replica database, which means that at some point of time, replication is not going to help you with write scalability. But what can help you with write scalability is sharding, which means that if you split your database into two parts, then you have divided your writes into 2 different disks, so you double basically your write capacity. So that is the other reason why, that is the reason why we want to do sharding. We can actually do sharding for read scalability also, because read scalability also divides the reads. But there is a trade-off here between what is the advantage of scaling read through replication versus how you scale reads through sharding. The difference is that if you scale reads through replication, you solve the geographical problem, which means that a person in Japan would have low latency. But you do have the consistency problem is that the replicas will always lag, so your data will not always be consistent. But sharding doesn't come for free either. I will talk about the trade-offs. In sharding, what you're doing is you're splitting your data into 2 parts, which means that if you're trying to create a transaction that wants to update both parts, then you have transaction consistency issues, which sharding will introduce as a new challenge, which replication will not introduce if you are trying to scale reads. I hope it's not too heavy, but I'll keep going. Maybe we'll answer questions at the end. If you look at systems, these are the questions usually people ask. How much consistency, how consistent is the system? Can I always get consistent data when I issue reads? Will it be responsive enough? Availability. Durability. If there is a catastrophic event, how much will we lose? Will we lose nothing, or will we lose the last few seconds worth of transactions, or will we lose the entire database? Are questions that people ask depending on their level of sensitivity. I'll talk about how we made decisions in Vitess with respect to these properties later, but these are some of the things. Like, for example, if a system is distributed, if you're a bank dealing with money, you always want atomicity. You always want, if you take money from one person and give it to the other person, you don't want money to get lost along the way. So that is something, so the transaction integrity and distributed atomicity are very important. Latency is another system which all web applications want. You never want to keep the user waiting for anything. And at the bottom is you want your system to keep running even if various things fail while you are running it. And a lot of systems promise all these things, but in reality, all they are telling you is that there will be cake. You cannot have all those things all at the same time. You have to choose at any point of time which is more important to you, and you have to be willing to give up something else for it. So that is basically what. If you go back to the CAP theorem, the CAP theorem itself is applies to a very small property of the system, but it kind of expands into other areas about durability and atomicity, which are actually kind of synonyms for consistency, which means that if you want more durability, if you want more atomicity, you have to give up on some availability properties. So I want to talk about some of the write options that we have and how they affect your availability. Paxos is somewhat a recent thing a lot of people are getting excited about. So how many of you know what Paxos is? Okay, very few. So Paxos is actually, I'll give you a 2-minute introduction of what Paxos is. Paxos is actually a write algorithm where instead of writing, if you decide to write something, instead of writing it in one place, you write it in many places all at the same time, as many places as possible. And what Paxos is that if you have written a data to more than half the servers that you have, let's say you have 5 servers, it's basically 5 master servers. If you have 5 servers and your data has been persisted in more than 3 of them, then the transaction is considered durable. If you've just written in one, you may lose that master, and if you lose that master, you could lose that transaction. So what Paxos gives you is basically a consensus protocol where it allows you, where it says that once this data is written in at least 3 of the 5 places, then your transaction is complete. And the whole algorithm deals with failure modes. What happens if this fails? What happens if that fails? They have recovery mechanisms for all those things. Which means that once a Paxos transaction is committed, there is nothing you can do to lose that data. If I was a whistleblower, I would use Paxos. Make sure that my documents are all over the place before I come out and say I'm done. Reveal what I have to say. But it has very, very high costs. The reason why it has high costs is because every write has to wait for that write to propagate to multiple places before a write is deemed done. So if you choose Paxos, you are going to you're going to pay you're going to incur high write latency, and you can compensate for it with very fast networks. But at the end of the day, you're still competing with the speed of write. Especially if you are going for Paxos, you're probably worried about major disasters, which means that you probably want your write to be geographically in a different location, maybe across the country or maybe in Europe or wherever else, depending on what your sensitivity is. The other write scheme is a master replica scheme, which most systems use, MariaDB, MySQL, all the common stuff that we use, which means that you write to a master, and as soon as it is written, the database tries to replicate that as fast as possible to as many replicas as possible. So if you compare Paxos versus master replica, they are very close in terms of durability. So if a master replica system fails, where the master suddenly fails catastrophically, you probably lose the last few transactions. So that is basically your exposure if you compare yourself with Paxos. But in a master replica scheme, you can go really fast, because as soon as you return to the master, so you're talking like few milliseconds transactions. Like in YouTube, I think our transactions usually like complete in 10 to 15 milliseconds, entire transactions. So, and then there is this thing called semi-sync replication, which is actually a fake Paxos, which means that as soon as I return to the master won't return my commit until it has confirmed that transaction has been received by at least one of the replicants. Which means that if one of the replicas says, okay, I received your transaction, then the commit returns, and then your transaction is deemed complete. For the longest time, I wasn't sure what value it brings. I think the main value it brings is that if there is a failure where a master is unable to replicate the data to a replica, then what this will tell you is it'll immediately sound the alarm saying that none of your transactions are completing, please go take a look. Then you can say, oh, looks like our master is done for, let's do a failover. So that is one thing that it is useful for. There is also multi-master writes, which have their pros and cons. I think the main problem with multi-master writes is the fact that there could be conflicting writes, and you have to figure out how to resolve them. So that is with replicated writes. If you go with sharded writes, then there's another set of challenges. The main one being transaction atomicity. If I'm going to take money from one place and give it to somebody else, that entire transaction needs to look atomic, which means that if I take money from an account, commit it, and then decide to go and put that money somewhere else, during that time someone can go read that account and see that the money has been taken, and then race ahead and try to read the other account where the money was sent, and the money may not be there already. If you want atomic distributed transactions, 2PC is the only known algorithm that achieves it. And the way it achieves it is using a very conservative algorithm, which is the prepare commit phase. And I won't go into the details, but what it has to do is basically prevent reads of those rows that it is changing. Basically, if I'm going to do a two-phase commit, I change row A and then change row B, and then do the prepare. As soon as I do the prepare, row B and row A are not readable until the entire transaction is done. So even though it looks awesome from the application perspective, it's all transparent. I just change data and commit, and everything happens atomically. There is a huge cost to pay in terms of scalability. Like for example, what if there is a hot row that changes too often? It's going to be constantly locked for read, which means that people will not be able to read that row if you're doing 2 PC transactions. So the alternative is to use sequenced commits. What it means in sequenced commit is that you decide on a very specific commit order after you've made your changes, such that if any of the commits fail, the database still looks consistent. If I have the time, I'll try to go into some examples that about how to achieve this. The other option with the sequence commit is to say that if I'm going to do something like money transfer, the best way to do it is do it as one transaction on one database where you take the money from the person and then create another word queue that says, make sure that this money reaches that person as part of the original transaction, and then have a batch job that picks it up and completes it as work. I'm kind of rushing because I don't want to run over. So read options are actually very more or less straightforward. Either you read from the place where the data was written, or read from a place that is replicating it. So if you go to the master and read, you'll always get consistent data. You'll always get up-to-date data. But you want to save your those reads. You want to make sure that do those reads only when it's important, because master, you don't want to overload the master, because then you'll have to start worrying about scaling it. If you go to replica reads, they're always available. The one technique that people have used to overcome reading from a replica and then trying to change the master, how do you know that the data you read from a replica is up to date with respect to the master, is called a CAS write, which is a compare and set. So when you read data from a replica, it tells you what version it is. And then you try to use that data to change the master. If somebody has changed the master, then the version number of the data has changed, and I try to change it, the master is going to say, oh, sorry, I've changed, so you'll have to read it. So if the data is not changing often, CAS writes are a kind of a very efficient way of reading from a replica and using that data to make changes to the master.
What does CAS stand for?
It's called compare and set, or compare and swap. It's a computer science term, which basically it's an atomic operation that lets you change data atomically, but based on a condition that the data is equal.
Very common CPU instruction in multi-threaded environment.
Yes. All right. I'm almost done, which is pretty good. So these are kind of the corollaries of the CAP theorem. So when you are evaluating a system, if they say that they are durable, they give you distributed atomicity, and they give you like really, really consistent reads, you can pretty much assume that that system is going to have higher latencies. It is also going to not be very tolerant to failures, and there is going to be availability trade-offs. Like if you have Paxos, for example, if you have 2 network failures, no writes will succeed really. Because if you have very specific partition failures, no nodes will be able to reach a consensus, and your system basically has to repair those networks until it can start accepting writes. But then you are guaranteed that you will never lose your data. Once it says that a transaction is committed, it is committed for good. No amount of node failures will you will lose. You won't lose data, no matter what kind of node failures you experience. And if you are going for availability, you obviously have to give up on some durability, some atomicity, and some consistency. But your system will have very low latency, which means that it will never stop serving you. And it's also very resilient to failures. Like master dies here, you immediately remaster somewhere else, and again you are serving again. If the master dies there, no problem. If network dies here, there's already 30 places that I'm replicating to. I don't care if data center goes down, just drain that data center, don't send traffic there anymore. So it's a much easier system to manage because availability, once you've made the consistency and durability trade-offs, you get really very good availability. And in my opinion, availability is more important than the other three. People don't get very disturbed if they lose their shopping cart, or I like the video, how come it's not there yet? I posted a comment, looks like it disappeared. Oh, let me post it again. So people are kind of tolerant to things that have failed in the last 5 seconds or 10 seconds. They're not very tolerant to them losing your entire account, but something that they did recently that didn't stick is something that users are usually willing to retry. So the Vitess project, when we made these decisions, we did not know about the cap theorem and all these great things. We just realized we just made common sense decisions, and then I found that, oh, there is a theorem that substantiates what we have done. So that's basically how we ended up here. In Vitess, our writes go to a single master, and those writes, and it is with semi-sync, which means that if a master is unable to replicate to other replicas, we will know immediately. So that's a very good failure mode detection for us. But otherwise, typically, like when data gets written on a master database, within 1 second, that data has reached all over the world. So that's typically the kind of delay we see, which means that for us to lose data, the master has to fail after it was written, and within those few milliseconds it takes for the data to leave the master to a replica. I think it has never happened in YouTube. To my knowledge, it has never happened. So we are very happy with our durability story, even though we write only to a single master. Sequenced commits for cross DBs. So what Vitess does is that if you are doing a cross database transaction, we will commit it in a very specific order, as long as you plan your statements in a way that it is self-healing. You will never have a problem. But typically, YouTube kind of traffic is people changing their own profiles. So most of the transactions are within the same shard, and those few that are cross-shard have self-healing properties. Therefore, it is something that I believe a good trade-off that we've made. Sometimes you want to read up-to-date data. Typically, a typical case is a user goes and changes their profile and immediately hit the refresh page to see if their profile got saved. So we kind of detect that as a special case, saying that, oh, if a user is seeing their own profile, don't read it from a replica because they may see stale data. Always send it to the master. And then all other reads are all over the place. We have replicas in, I don't know, Asian countries, European countries, and all those people have really, really low latency because the data that they have to access is right in their home turf. So these are the Vitess choices. So I'm going to conclude with some crazy ideas that I've been having that I believe we should do with databases like MySQL and MariaDB. Paxos is actually a fantastic master election algorithm. Paxos actually, the protocol, you can actually elect a master within milliseconds. They have to, because a Paxos master election is a Paxos transaction. If a Paxos transaction cannot complete in like 100 milliseconds, then the system is not going to scale. But electing a master in 100 milliseconds is something we have never done with MySQL or MariaDB, but we can. Like, let's say a master is accepting writes, and for some reason there is a failure. What if we knew that there are 2 or 3 other slaves that are ready to become masters? The only thing we have to verify is that, do you have the latest transaction from me? Okay, you go master. I'll go fail, or I'll go become a replica. What this means, it will give us huge uptime if we manage to implement this in single master writes, which means that a master failure is almost a non-event. It says, oh, master down, boom, within a few seconds, within a few milliseconds, typically, ideally speaking, another replica has become the master, and then you send the writes to that new master. Google, we have something called the decider, which used to do a remaster, automatically detect a master failure and elect a new master within about 30 to 40 seconds. And now we have a new version that we are prototyping that can do this in about 5 seconds. And we are still not happy. We want it to be within a second.
So we added to MariaDB the new command, wait for global transaction ID. So you can just, if you know the global transaction ID in the master, you can just ask which slave has it, and you can immediately switch to that.
Cool, yes. So all we have to do is add a Paxos protocol to elect a master, so they all talk to each other and say, okay, I'll be the master, everybody else agrees, and boom, then that guy becomes the master. I believe we can do that in such a way that the system doesn't even notice. There's still some protocol where the master has then published that it is the master and the clients have to pick it up and say, okay, connect to that. But that is something that plumbing is something we can do on top of that. But we are getting there. It's getting, the global transaction ID is one of the best things that has happened to the MySQL MariaDB world. Because without that, a master failover is a complete nightmare. I mean, we used to take like an hour to do a failover, because you do a failover, you go chase down all the replicas, and then you have to have the file name position and position, and then like individually go and update those things.
So what kind of storage and networking option do you have? And did you get a chance to compare network storage versus local storage options?
Yes, I will. Let me finish this and then I will answer your question. So the other crazy idea is what I call as P2P replication, which is actually kind of an extension of the global transaction ID. So the global transaction ID, the way it works is you connect to the master and you keep on receiving next transaction using the global transaction ID. But you don't have to get that transaction from a master. You can get that transaction from anybody who has received it. So, like, if I am a replica, the only thing that I crave for is give me the next transaction ID. Give me the next transaction. So all I need to say is publish screen saying that I want transaction number 12, and if somebody else has transaction number 12 sitting right next to me, I can get that transaction from them. I don't have to go to a master. So if we did this, then there is no need to, when you do a remaster event, you don't need to go to all the replicas and point them to the new master. The replicas are just feeding off of each other with the latest transaction, and so this will become kind of a zero config situation. And P2P is a proven, well-known protocol. We just have to implement it to our databases. These are kind of crazy ideas. They probably have practical issues and limitations, but I think these things would make systems a lot more robust and better performing and easier to manage if we kind of make them right. So that concludes my my talk. So I will now answer questions. Let me answer your question first.
What kind of storage as well as networking options?
Correct.
Do you
Yes.
have? And in terms of storage options, did you get a chance on comparing network storage like cloud storage versus local storage?
Correct. So the question is, do we have any, do we use network storage versus local storage? We don't. We are very, very, very latency sensitive. We cannot afford to. I mean, like we don't even want to write to another. We don't even want to wait for a write to reach to another. Actually, we have the semi-sync, but that's probably the only network traffic that you incur when we do the writes. Otherwise, we do SSDs. We want writes to be really fast.
Local, right?
All local. The only thing is the semi-sync, which basically makes sure that the transaction has been received by a second replica.
So that's in your data center?
It's within the data center. And like I said, we are not very paranoid about losing the last few transactions. It's okay if we lose it.
But in terms of video, I mean, the size of those files are huge.
Correct. Vitess does not work with videos.
It's like, in terms of storage capacity should be, I mean, very big.
Yeah, the Vitess doesn't deal with videos. There's a different system for that, and that is managed through Google's internal storage. It's a file storage, not even a database. Yes, sir.
Distributed master election is proven to be undecidable. What's the consequence practical for you on the Paxos master election?
I actually did not know about this. I should read that paper.
It's proven for 25 years. I can show you. It's distributed master election on non-reliable network. If the network cannot be guaranteed to be reliable 100%, there does not exist an algorithm for distributed master election.
So I believe that.
I'll give you the reference.
Yes, I will definitely want to read this. So I believe that it should be the same symptoms that Paxos suffers from, because Paxos is a distributed master election algorithm. So there is probably pathological cases where, actually I even talked about those. If there is multiple network failures, there are cases where a system cannot reach consensus. And at that time, just like Paxos will freeze up, the master election will also freeze up. And the way I would solve that problem, I'm a practical guy. If the system is frozen and it's just unable to choose a master, okay, I overwrite, I say you are the master. Let's go with it. That's the way I would solve it. But yes, I think the proof would be if there is multiple network partitions and no single group can achieve majority, then you cannot come to a consensus. I assume that's what the paper tries to prove.
I will give the reference.
Yeah, I will take a look at the reference. Yeah.
So how do you scale your cluster? How do you scale your cluster? It depends on the demands. You might scale up your, not scale up, scale in or scale up your cluster. You don't do that at all?
We do scale our cluster. We use replication and sharding. When we want to scale our reads, we use replication, and when we want to scale our writes, we use sharding.
Those are all manual.
Vitess actually automates that part. That's basically what our tool does.
I understand sharding is automatic, but I mean scale is. For example, I have doubles the size of my cluster, so in that sense, it's manual. You decide when to go or where to go.
Yes, there are some decisions that you still have to make. There is no free. Any system that claims that we will automatically figure out what you do and then we scale it accordingly is a system that for which you can find a situation where it will make the wrong decision. That's one of my pet peeves about even the MySQL or MariaDB optimizer is that there is always a pathological case where the optimizer makes the wrong decision for a query. But then the question is, otherwise you have to do all the work, you have to make that decision all the time. So it's kind of a trade-off at the end of the day, how much control you want to have versus how much automation you want to get. So they are always going to be conflicting with each other.
So did you say you have only one master in YouTube or other number?
No, we have one, we write to a single master. But we have many databases, we have many masters.
How is the configuration of this single master?
What do you mean by configuration?
Yeah, how big is it?
I actually don't know what hardware it is. It will probably be a typical modern day machine with, I would say like 20, this is Google, so we have varying hardware characteristics. A machine could have 20 to 40 CPUs, could have a few gigabytes of RAM and disk. The way Google works is you basically say this is what I want, and if there is a machine that has twice the capacity, then it will put 2 of my things in there. So you basically never know what hardware you're going to end up with. The only thing it guarantees you is that I ask for 8 CPUs, you will have 8 CPUs. I ask this much memory, this much disk bandwidth, so you will have those. But there is no guarantee about what hardware you're
So
going
those
to
machines
have.
are bare metal or container?
Yeah, I don't know what they do. I think they use containers now. Yes.
So the Paxos, right now you say the crazy idea about electing master election.
Yeah.
Does Paxos can do the master election now or not?
Paxos can do. Paxos is designed for master elections.
Oh, okay.
So even the decider product that we have uses Paxos to decide who the master is, except that it's an outside agent that's acting.
So your crazy idea is make it a millisecond election?
Make the master itself, make the potential masters themselves do that decision. So which means that a master can get elected every few seconds. It doesn't matter that. There is no need to keep a master running for months and rely on that master being up. We can make this decision every few days. It doesn't have to be every few seconds. If the election is only like 100 milliseconds. Yes. Thank you very much.